Okay, so welcome back to another video. So in today's video, it's going to be just a really simple question. What is the modulus of gamma of I? So we know that modulus is technically another way to state the absolute value, or in other case in applications known as distance. So we'd like to calculate the distance of the gamma of I. And of course, there's actually a couple properties we'll be using in terms of course, gamma functions itself. It's also another formula we'll be using. We'll also be using also some properties using dealing with conjugates of complex numbers. So that's a neat thing to observe. So let's actually get started. The way to define a modulus is basically if I take some complex number z, so the modulus of z, or the absolute value of the complex number z being equal x plus I times y, where x and y are real numbers. So the modulus of x plus I times y is basically just equal to square root of x squared plus y squared. We just have that definition like in check, so we'll just have to keep that in mind. So the formula we'll be using is we're going to be using Euler's reflection formula, and I proved this formula a couple times. Well, in the video, I didn't mean to say it a couple times. I used this formula in a couple videos, but I did a video on proving the formula itself. So if you want to check that derivation, the video that will be in the link in the description. That itself, the formula is defined as gamma of z multiplied by gamma of 1 minus z is equal to pi, then divided by sine of pi times z. And of course, we know that here we have gamma of I, so we'll be just replacing everything in terms of I for z. So therefore we have gamma of I, and then gamma of 1 minus I. So that would just be equal to pi, and then divided by sine of pi, then times I. We just replace the z with our I, since the I is the complex number we're working with. Next is I'm gonna establish the relationship. And actually, in the previous video that I uploaded, we did use this relationship, and I did the fast proof of this. So you can check that out if you want to see that. But we're going to be using the relationship that sine of pi times, or not pi, excuse me, we're just using the variable x, for example, to state this, what we're using with, for example. So sine of x times I is equal to I times the hyperbolic sine of x. So what that means is that we'll just replace the sine of pi I. So over here, this will be, now in this case, I times the hyperbolic sine of pi. So then let me just rewrite this again the second time. Therefore, we have that this is just pi, and then divided by I times the hyperbolic sine of pi. So a property we'll be using for gamma functions is that we know that gamma of z, z plus 1 actually, is equal to just z and then multiplied by gamma of z, where z is the complex number. So in this case, we have gamma of 1 minus I. So really, in this case, we can just write this 1 minus I gamma, and then putting in the pieces together, really our z would be the negative I in this case. So then this will be negative I, and then multiplied by the gamma of negative I. And so what that means is that I can just replace the negative I gamma, the negative I times gamma of negative I, replace this with here, and so we get that. So far we have the new derivation that negative I times the gamma of negative I multiplied with gamma I. So far we have so far concluded that that's just pi divided by I times the hyperbolic sine of pi. And of course we have a we have a negative I to both sides. So what this means is that I can divide this by both sides by negative I. And then coming down to this line is that we have gamma of negative I, then gamma of I, that's just equal to pi and then divided by, so that means we have negative I times I, so negative I squares, but we know that that's just equal to 1, so it's just the hyperbolic sine of pi in the denominator. Okay, so now the next step is that so far we showed that gamma of negative I times gamma of I is equal to pi times the hyperbolic sine of, or pi divided by hyperbolic sine of pi. Notice that negative I in this input over here, it's actually the same thing as its as the conjugate of I. Since we know that the conjugate of I, or the conjugate of a complex number, for example, so x plus I times y, the conjugate of that is just replacing the sign of the imaginary unit. So this, in this case, the conjugate of the complex number z is just x minus I sub I times y. Here, negative I is a complex number, so if we can rewrite that negative I as the conjugate of I. So this means, so we have gamma of I conjugate multiplied by gamma I, and so far that's just equal to pi divided by the hyperbolic sine of pi. Okay, and so now next thing I'll do is that I'll take the modulus of both sides. So we'll take the modulus of the left hand side, and then I'll take the modulus of the right hand side. Now what I can do is that we can use the properties with absolute values, is that it can be multiplied as a product of absolute values. So we have the absolute value of gamma of I conjugate multiplied with the absolute value of gamma I. And of course, we have not done anything to the right side of the equation yet, so that still remains the same. Okay. And now here's some properties about how the conjugate works with gamma. We know that the gamma of z conjugate is basically, it's the conjugate of the entire gamma function. Okay. And then another thing we know is that the absolute value of z conjugate is actually also equal to just the conjugate of z itself. If you think about it in this sense, we have that if I were to replace, the conjugate with x minus I sub I times y, and we put those back into the formula, we just notice that we have like squares and then the square root of that. Basically, everything is positive. It just remains the same thing, just with dealing with the formula with just the regular complex number instead of its conjugates. So that's why we should see that these two equal to each other. So these two properties established, and so we're just about almost done with the proof, or rather the proof with the calculation. Let's rewrite from the other line, this line over here. So we have gamma of I, the gamma of I conjugate of I, and so that's multiplied with gamma of I, the modulus of gamma I. So using these properties, we know that this is just gamma I, and then the conjugate of that, and then we multiply this back with gamma I, the modulus, and then using the establishing this, well, really, I should have wrote this a little clearer. It's the conjugate of the gamma function, like this, not the conjugate of the modulus. Sorry about that. And now everything will come to make sense. So we just use this property for here. So we know that this is just gamma of I, and then multiply this again. So really you can just write that as a square. And then the right hand side, so far, we have not done anything just yet. Well, actually, technically yes, but I didn't really show the work. If you actually just calculate the modulus of this is just basically the same thing except the absolute brackets. So it's just pi divided by hyperbolic sine of h. And basically that's it. So just take the square root of both sides, and we have come to the conclusion that this is just the square root of pi divided by hyperbolic sine of h, or of pi, excuse me. And there we have it. That's pretty much the, I wouldn't say pretty much, but that's our answer to the given question up above. The modulus of gamma I is equal to the square root of pi divided by hyperbolic sine of pi, like so. All right, now that's pretty cool if you ask me.